Example 3. Evaluate each expression without using a calculator. In part A, we are looking for the cosine of the sine inverse of 2/3. Okay, so when you look at this, okay, if you followed the order of operations, you would start inside the parentheses, you would compute this, and if you look at this quantity inside the parentheses, you have sine inverse of something. So remember, sine inverse is going to return an angle. Okay, so this is going to be some angle theta, and then you're going to take the cosine of that angle. Okay, and so then the answer is just going to be a number. Okay, so that's kind of the idea here. The answer will be a number as opposed to an angle. Okay, so keep that in mind. Okay, again, we are going to start inside the parentheses. Okay, so let's look at sine inverse of 2/3. Okay, this is going to be some angle theta, like I said. What this is, okay, this is, if we're dealing with sine inverse, so we'd have to go get its domain and range. Okay, if you flip back to page 7, the domain of sine inverse is -1 to +1, including the endpoints. The range, the type of angle that is returned, is going to be from -π/2 to +π/2, including those endpoints. Okay, so sine inverse of 2/3 is the angle between -π/2 and +π/2 whose sine is 2/3. Okay, so if you jump to the unit circle, and we need to be looking at the right hand side of the unit circle for sine inverse, okay, you need to be looking for an angle whose y coordinate is 2/3. Okay, so when you do a quick scan of the unit circle here, none of these angles that are called out have a y coordinate of 2/3. Okay, so what's going on here, if we go back, we need to check the domain. Okay, you're plugging in 2/3 to the sine inverse function. That's a valid input because 2/3 is between -1 and +1. Okay, so let me just recap here what's going on. Okay, we know that sine inverse of 2/3, that is going to be some angle between -π/2 and +π/2 that has a sine value of 2/3. Okay, we don't see one that we can read off. We can't read the angle off of the unit circle. Okay, that doesn't mean that this value does not exist, because we actually are allowed to plug in 2/3 to the sine inverse function. It is a valid input. Okay, so what's going on here is that we have to use a different method to figure this out. We cannot rely on the unit circle. Okay, all right, so let me show you what you need to do here. Okay, so since we're dealing with sine inverse, I'm going to move this information off to the side here. For sine inverse of x, we do need to keep track of the domain, more so the range. So I'm just going to jot this down over here. Okay, so now I am going to erase this. Okay, and we're going to begin anew. Okay. All right, so what we're going to do, okay, we're just starting over. Okay, we're beginning with the quantity in parentheses. I am going to call that theta. Okay, so we're going to let theta be the sine inverse of 2/3. Okay, so, inverses are tricky. Okay, we don't like, well, I don't like dealing with them. So to kind of get rid of it, what you can do is you can take the sine of both sides. Okay, so the sine of theta is going to be equal to the sine of the sine inverse of 2/3. Okay, so sine and sine inverse undo each other. Okay, so what we can conclude is that the sine of theta is equal to 2/3. Okay, so what we're going to do is draw a right triangle that illustrates this situation. Okay, so we have the sine of some angle theta. Okay, remember this quantity in parentheses is representing the theta. The sine of this angle is 2/3. Okay, we have to take into consideration the range here. Sine inverse is going to return an angle between negative pi over 2 and positive pi over 2. So again, that's quadrants 1 and 4. Okay, so when I draw out my x and y axes here, I need to concentrate on quadrants 1 and 4 because that is the range of sine inverse. Okay, so since the sine value here is positive, sine is positive in quadrant 1, not quadrant 4. Sine is negative in quadrant 4. So when we draw our right triangle, we are going to draw it in quadrant 1, not quadrant 4. This is why you have to take the range into account here. Okay, so draw your angle. Okay, this is going to be the theta value that you're looking for. Okay, so then we'll construct the right triangle. Okay, so from the terminal side of the angle, I'm going to draw straight down to the x-axis to make my right angle, and there's my right triangle. Okay, we know that the sine of theta is 2/3. Okay, this is the opposite over the hypotenuse. Okay, so you need to label these sides. Okay, the opposite side is 2. The hypotenuse is going to be labeled with a 3. Okay, so let's do this. If we go straight across from theta, this is the opposite side. It needs to be labeled with a 2. Across from the right angle, this is the hypotenuse. It needs to be labeled with a 3. The remaining side is the adjacent side, and we need to calculate what that value is. Okay, right triangle, we're going to call in the Pythagorean theorem. So c squared is equal to a squared plus b squared. Okay, and we are looking for the adjacent side. Okay, so I'm going to plug into this the hypotenuse, which is c. This is going to be 3 squared. That's equal to a squared plus the opposite side squared. Okay, so I'm going to get 9 is equal to a squared plus 4. Okay, so I'm going to get that if I subtract 4 from both sides, I'm going to get that 5 is equal to a squared. Okay, if I want a, I have to take the square root of both sides. Okay, don't forget the plus or minus out front. Okay, so a is either positive or negative square root of 5. Okay, you have to determine the sign. Okay, you can't pick both. The adjacent side lies along the positive x-axis, so you need to pick the positive value. Okay, so this side is the square root of 5. So we have constructed the right triangle for theta in quadrant 1, and we know that based on our drawing here, we've got the sine of theta is 2/3, and we have done the work to get the remaining side. Okay, now that we have this right triangle, we're going to use it to solve the problem. Okay, I am going to rewrite the original problem. We are trying to compute the cosine of the sine inverse of 2/3. Okay, now just follow me. Okay, remember, we said the quantity inside is theta. Okay, we called this theta. So this is going to be equal to the cosine of theta. Okay, we made a right triangle drawing for theta. Okay, we can now find the cosine of theta based off of this right triangle. Cosine is the adjacent over the hypotenuse. Okay, so if you read this off the right triangle, the adjacent side is the square root of 5. The hypotenuse is 3. This is the answer. Okay, that we were looking for. Okay, the cosine of the sine inverse of 2/3 is equal to the square root of 5 over 3. I know that the instructions say not to use a calculator, okay, but you can check yourself. Okay, you do have to show all the work, but you can check yourself to make sure that you are correct. Okay, we just need to compare the decimal expansions. We're going to type in the original problem and then type in our solution to compare the decimals. They should be the same. Okay, when you plug this into the calculator, this original statement, your calculator needs to be in radians. Okay, there is no mention of degrees, so you need to go with a radian measure. I'm already in radians here. So let's type this in. We're going to do the cosine of the sine inverse of 2/3. Okay, so here's the decimal expansion, and then we need to pop in square root of 5 over 3 to see how that compares. So square root of 5 over 3, same decimal expansion, so we are correct.